So we started off, so we've talked about what stress and strain are, how to build a stress, how we basically almost just talked about language so far, about the language of three-dimensional stress and strain, what a tensor is, and how to manipulate a tensor to get it in the coordinate system that we're interested in, and probably most importantly, this concept of what a state of stress is. So now we're going to talk about stress-strain behavior of soils. And I hope to dispel, I've come to the conclusion that we really do everybody a disservice by using the E log P method as the way that we're going to, that we teach you all at the beginning about, how we deal with stress and strain. No, there's no IME class here for another until 6 o'clock. Okay.
No, because it said 5 p.m.
Oh, well, it's not in here. I'm sorry, yeah, that's actually, clock's not right. It's actually after 5 now, right? Yeah. Yeah. So stress and strain. We start off with these E log P curves, right? You all know this, right? Where we do, whoops, how come you didn't do what I wanted you to do? Where we tell you, this is going to be log of sigma prime, and this is either the strain or the void ratio. And we say, yeah, this is what what the stress strain curves looks for isola. You got C sub C. It's like, all right, that is a really bad thing to do. So what we're going to do is, like all good graduate classes, we're going to do, I hope to, by the time we're done today, we're going to convince you that everything we told you before was wrong. Okay, and that's not the way things really are. So. Anyway, when we do get done with this, so we're going to start off talking a lot about elasticity. That's what this section's on. So you need to be able to understand what elastic constants are. Specifically, I want you to know these 4 constants. Shear modulus, bulk modulus, the shear modulus, Young's modulus, and Poisson's ratio. 2 of those you already probably have a pretty good handle on. The other 2 you probably don't. You definitely need to understand what those are by the time we're done with this section. Then we're going to talk a little bit about the stiffness matrix and the compliance matrix and how they relate stress and strain. I just want you to be able to describe those. Notice it doesn't say invert the stiffness matrix. I just want you to be able to describe what they are. I'm pretty careful about the verbs I pick. Describe is not the same as define. It's not the same as compare and contrast. That's what I expect you to do. I bet you to be able to write the stiffness matrix for an isotropic material. We're going to talk about what that means. Plane strain conditions are really important. You need to be able to define what plane strain conditions are. And then you need to be able to, this says derive, but that also means simplify our three-dimensional stress strain thing when it's in plane strain. Because plane strain is a three-dimensional stress strain state, but it's a simplified one, and the matrix gets a lot smaller. And then be able to explain why it is we use plane strain conditions anyway, because there's a lot of cases where it's a good model for soils. All right, so we're going to start with a really simple example. I'm going to start with a little cylinder. So this is your concrete cylinder in you're testing in a concrete testing device, or it's a unconfined compression test for geotechnical engineers. But we have a cylinder of soil, and we're going to put a uniform stress across the top of it. So this is our real model, and then we're just going to draw it in 2 dimensions because we're lazy. It's going to start off with a length L0 and a radius R0, and we're going to squeeze it on top. We're going to put pressure on the top, or stress on the top, and it is going to deform. It's going to get shorter and fatter, right? And how much is how are we going to calculate delta L if this is an elastic material? And Hooke's law applies. Oh, we got the radius change too. So we're going to calculate delta L. So the strain in the vertical direction is just going to be change in length over the original length, right? Delta L over L0. And the relations, in the strain in the radial direction, it's negative because compression is positive, right? So the strain in the radial direction is just the change in the radius over the original radius. So that's the strain. We're going to relate it now we want to relate that to stress. Well, broadly speaking, there's 3 different stress strain curves you can have. This is a elastic, perfectly plastic curve. And we have an engineering material that behaves pretty close to that. One we can certainly model like that. What's the material that has a behavior that looks pretty much like that? Goes up, very elastic, and all of a sudden yields, and it's got this real long yield curve. Steel. This is like, you know, a real steel stress strain curve would come out like that, and it would go something like this. But you can model it definitely like that, and that's how we model steel. It's a very good model for steel. Then we have other materials that look like this, that we would call strain softening. Strain softening. So what do I mean by strain softening? What's happening as we get additional strain in that material? How much strain? So let's put 3, 2, 3. Okay, see, these are 3 different increments of strain. This is all delta epsilon. Same increments. If they aren't exactly the same, pretend they are. All right? So I've got the same increment of strain in each one of these. Do I get the same amount of, does it require the same amount of stress or to get that amount of strain in each one? No. Look at this. Right? Much less. So as the strain's going up, the material is softening. In other words, the material is getting more, you're getting more strain for the same amount of stress. That's a strain softening material. What material looks like that? Anybody in CMT concrete? This is a stress strain curve for a concrete cylinder, right? It's exactly what it looks like. Fractures right here, right? So as you get increased stress, it actually gets softer. The modulus goes down, right? And then the third kind of material, whoops, going the wrong way again. The third kind of material this one's actually a little complex because it starts off kind of linear down in the bottom and then softens, but then it gets stiffer again. So this is a strain hardening material. It actually starts off as a strain softening material, but the main part of this curve here, notice that as the strain increases here, it's getting stiffer, right? The curve's getting steeper. So this is a strain hardening material. So what looks like that? Soil. All right? So the slope of this line right here is, in the case of, if we're still talking about the cylinder, is Young's modulus, which we can call delta sigma over delta E, or if we do it in a differential sense, it's going to be d sigma d epsilon. So that is Young's modulus for a linear elastic material. What about for this non-linear material? How do we define the modulus for that? So the modulus is just the slope of the stress strain curve. Well, if I'm looking at this point here, the tangent modulus, and some people would call it the true modulus of that, is still d sigma d epsilon. So it's basically a tangent at that point. And that is the incremental amount of that defines the incremental amount of stress you're going to get for a small change in stress. Well, that's nice if I'm going from this point to a point right next to it, but if I'm going from 0 to there, right? What good does that tangent modulus do me? Well, if I'm going from, if I wanted to know the change in stress, over this change in strain, what I really need to do is I've got to integrate, from 0, let's call this epsilon 1, from 0 to epsilon 1, right? D sigma d epsilon times d epsilon. And I've got to integrate this as the slope changes all the way along, right? Well, that's an integral, and we're engineers. So we don't like doing that. And if all I wanted to know was what's going on at that point, there's a simpler way to do it. I could just define a secant modulus now, which is going to be, it's just going to be this slope. And now, this delta sigma, this is much easier because now delta sigma is just equal to the secant modulus. the secant modulus times epsilon 1, right? So it's much easier to calculate the strain at that point. Of course, the trouble is that's only the secant modulus for one point, right? If I wanted to know what was going on down here, I'm going to have a different secant modulus. So this you got to make sure you got to make sure you understand the difference between a secant modulus and a tangent modulus. And in the case where it's a linear function, then this is both the secant modulus and a tangent modulus, so that's nice. But if it's nonlinear, we can define the modulus, these are the secant modulus or the tangent modulus, and there's clear advantages and disadvantages to each. So the big lesson here is don't confuse the secant modulus versus the tangent modulus. The tangent modulus is really the true instantaneous modulus, if you want to think of it that way, and the secant modulus is just a convenient shorthand to get from one point to another point without having to integrate. And if you're dealing with, if you're always dealing with strains in, say, a region in here, if this is the only region in which your problem has strains that you deal with, then you can define it, I mean, the error you're going to get by having a secant modulus is not exactly right, might not be too large, and that'd be easier. It's way easier than integrating. But if you have to deal with the whole stress strain curve, then that's not going to work for you. Okay? All right, let's make sure we understand the difference between elastic and plastic strain. So elastic is reversible deformation. So if you unload, you recover it. Linear elastic, this is the gross definition for linear elastic, which says, and we'll illustrate this, and it's easier to understand illustrated, but something's linear elastic when successive effects, when superimposed, leave no indication of their sequence. I got that direct out of a engineering mechanics text. But it means basically you can change the order of things that you do things and still end up in the same point. Doesn't matter which one you do first, you always end up in the same place. It's easier to look at it and see what it says. We'll look at a picture of it in just a second. So and plastic strain is irreversible deformation, or deformation you don't recover when you unload. So let's look at them. So here are these. I'm just going to use these two stress strain curves for right now. So I'm going to go back and do it again. Watch the little arrow here. Get my laser pointer. So watch the little arrow here. So here's the little arrow. Whoops. So I'm going to load and I go up the curve, right? And if when I unload, I come straight back down that curve, that's elastic. I loaded I loaded up to a certain strain level. I loaded up to this strain level right here, and when I unloaded, I recovered all that strain back down to zero. That also happens to be linear elastic because we're on a line. But I could also load on this curve if I loaded up to this point right here. Now if I unloaded and it went back down the same curve, that's still elastic. It's not linearly elastic. And I'll show you that successive, let's just divide this thing into two parts. Let's divide it here, and this one's the same amount, and here. Okay, with the linear, so if these delta epsilons are the same here, notice here I'm going to get a delta sigma, and these two will be the same too, because it's linear elastic. So I could take the change from, and what it says by superimposing things, I could take the change here first, and then take the change there, and I add them together. I'm just going to still get 2 delta sigma. It doesn't matter which way I do it, I'm going to end up with the same amount. In fact, these don't even have to be the same. However, if I go to the nonlinear one, notice that in this case, delta sigma 1 is going to be less than delta sigma 2, right? Same amount, same increment. So I can't swap, what it's saying is I can't swap these two changes in strain and still come up with the same stress. If I did the one that's softer first and then the one that's stiffer, I'm going to have a different answer. So that's what that successive increments can be superimposed. The easier way to just look at it is realize that it's not going up a straight line. So what, in other words, what's happening up here is not the same as what's happening down here. Where here, what's happening in here is the same as happening here, same as happening over here, same as happening there. So that's just elastic. So you don't have to have, it is possible to have nonlinear elastic behavior. It doesn't happen often, but there are materials that don't have a linear stress strain curve, but they recover all the strain that you put on them. The most common thing is to have a combination of elastic and plastic strain. So this is a very common occurrence. Here's our steel again. We're going to load up this linear portion of the curve. We get to here. What happens if we undergo more strain now? We're going to move across this horizontal part of the curve, right? And we're going to go out to some point out there. Let me mark that point. So we're going to go out to this point right here. Now if I unload, if this is steel and I unload, what's going to happen? Am I going to go back here and down? No, I'm going to come down on a curve that should be, if it's steel and you haven't gone too far, if you haven't undergone too much strain hardening, which does happen in steel, you should come down in a line that's parallel to the first one. So what kind of strain is this right here? I loaded, I crossed over the elastic part of the curve, I unloaded. That strain's still there after I unload. So what kind of strain is that? Plastic strain, that's correct, plastic strain. So this is plastic. I got to learn not to write near the bottom of the thing. Okay. And what about, now, the peak strain we had was right here, right? That was the maximum strain we had. So if I divide this up, I'm going to be smart this time, put it up here. What kind of strain is this? That was recovered strain, right? So that's actually the elastic part of this strain. That was the amount that was recovered. And by the way, that will be the same as this right here will be the same as that if those two lines are parallel. Okay? I think now I want to erase the... Okay, well here's my nonlinear stress strain curve. So now if I load up to this point, let me mark that point, and now when I unload, I could come down in almost any arbitrary curve. It's very common on these materials to have a fairly linear unloading curve, even though the loading curve was not linear. That's fairly common. And in this case, this distance right here is going to be the plastic strain. And this distance right here would be the elastic strain because that's the amount that was recovered, right? They don't necessarily need to follow a linear. I mean, the unloading curve could, look something like that too. I mean, that's possible too. So it's pretty simple. Elastic is recovered strain, plastic is non-recovered strain, irreversible strain. Okay, let's just do some definitions here. Because this is the material we're going to be talking about now for some period, not for the whole class, but for a lot of, we're going to be, this is one of the materials we're going to talk about. So homogeneous, isotropic, linear elastic. We've already defined linear elastic, so we don't have to define that again. But homogeneous means it's the same in it's the same everywhere. So homogeneous means the properties are the same throughout the material. Does that mean it's a uniform material? No. Think of these composites you have right now, where you've got layers of you see these composite sheets where you've got basically layers of either carbon fiber or fiberglass or something in a matrix, but the sheets are all laid out. So every point I go in there, it's the same material, right? In a macro sense, it's the same material. I've got this material that's got carbon fibers in these directions, and it's in a matrix, and it's the same everywhere, but it's not the same in X and Y directions as it is in the Z direction, because one of them is a bunch of layers where the fibers run this way, and the other one goes across the fibers. It's not the same in every direction. Or even think about your clothes or a piece of paper. Paper or plastics that we use in geosynthetics, they have what they call a machine in a cross machine direction, because or the fabrics are woven in the woof direction, and they stretch one way and not the other way, or they're different. The fabric is the same everywhere, but it's not the same in the X and the Y direction. So don't confuse homogeneous with isotropic, because iso, same, tropic is direction. So isotropic means the properties don't vary with direction. So like wood might be homogeneous but not isotropic because it's got grain and stuff. Soil is often really, I mean, the simplest model of soil is homogeneous and isotropic, and we use that a lot. But really, soils are often layered in the horizontal direction due to deposition, and then they could be homogeneous but anisotropic. So aniso, let me write that one. If you put an an in front of this, it means it's not the same in both directions. If we have a material that is homogeneous and isotropic and linear elastic, we only need two constants to describe its stress-strain behavior in 3 dimensions. Any two of the elastic constants will do. So we'll talk about those now. So let's go back to our uniaxial loading case. Now we defined the strain in that, and let's talk about stress versus strain. So we define the strain as delta L over L0, and the relationship between the stress and strain then for this case is that the strain is equal to the applied stress divided by Young's modulus. We all know this, right? So E is Young's modulus. So Young's modulus only defines the change in stress and strain for the conditions where we have uniaxial loading, all right? Where we have a sigma applied on top, and on the sides, sigma is equal to 0. So this would be sigma 2 is equal to 0 and sigma 3 is equal to 0. That's the only time when this relationship is true. So you have to have the boundary conditions correct for this to work. The change in radius, this is when we squeeze a cylinder and it goes out in the sides, what do we call that? There's somebody's effect. Poisson's effect, right? And we call it Poisson's effect because, back in that time, people had lots of time on their hands. If you were rich, you could think about these kind of things. And the Poisson's effect, which is a measured observed behavior, is that the amount something squeezes out to the sides when you push on it from the top is proportional, that strain is proportional to the vertical strain by some constant. Or we can rewrite that, and that's Poisson's ratio, because Poisson figured this out, and it's just an observed behavior. So those are two of the elastic constants that we can use to describe three-dimensional states that relate three-dimensional stress to three-dimensional strain. Now, these two simple relationships here only apply under this boundary conditions, but we can use those constants for any boundary conditions. It's just that the relationship's not quite as simple. So let's look at we talked about Mohr circles and why we want to do them. So let's watch what's going on in a Mohr circle in this state for unconfined compression. So when we start with unconfined compression, I take my cylinder and I set it in the loading machine, and before I put any load on it. This is what the Mohr circle's like. I have no shear strain, and I have no normal stress, right? Now, as I start to push on the top of the cylinder, right, what's changing? The normal stress on the top. What's happening to the normal stress on the side of the cylinder? Nothing. So it's still equal to 0. So as I'm going to start off with this point here, and then as I increase the load a little bit, I'm going to get that Mohr circle. I'm going to plot the tops of these Mohr circles for a reason I'll show you in a minute. And if I increase the load a little more, I get a different Mohr circle. Notice that nothing's changing down here. The horizontal stress is still 0. I want to plot that little point right there. And I keep doing this. And eventually, it'll fail, right? Notice that let me just ask the question: is there any shear in this? Is this a sample at this point where I've loaded it on the top but not on the sides? Is there any shear in that sample? Did I apply any shear loads to it? I just applied normal loads to it. But you tell me that sample is in a state where it has shear? Sure. What's the maximum shear stress it has? It's right here, right? That's it right there. So I think this is a thing that confuses a lot of people. And you think, oh, I'm just uniaxial loading. I'm not doing any shear. I'm not putting any shear load on that thing. Well, the load you're applying is a normal load and putting a normal stress. But the state of stress has a significant amount of shear. In fact, that concrete cylinder fails in shear. It's shear that it fails under. It doesn't fail under a normal stress. It may have failed under a normal load, but it's not failing under normal stress. It's failing under shear stress. And by the way, we taught one of the reasons, the reason I'm plotting the tops of those circles is another way to talk about this stress path. This would be a stress path. And drawing a whole lot of more circles gets cumbersome, right? If I left all those more circles on, you'd have a whole bunch of more circles on. So when you want to look at the way a path that, some loading path that some material undergoes, sometimes it's much more convenient just to draw this line that is just a plot of the maximum shear stress versus the mean normal stress, right? So this is actually, you'll talk about this next quarter, this is actually a PQ line or PQ diagram. Because what I'm plotting there is I'm plotting the mean normal stress, right? These were the centers of the circles, right? This is the center of the circle at this point, right? So that's sigma m, and this is the maximum shear stress. So it's lots of times we call sigma MP, I'm sorry, Q, no, P. And we'll call the shear stress Q, and this is a PQ diagram. You're going to talk about that next quarter. It's just a shorthand way of not drawing a bunch of more circles, because if you have a whole bunch of changes of stress and you got more circles all over the place, you can't see what's going on. But it's kind of, it takes a little while to visualize what that means. All right, that was a little aside. Okay, so realize that even when we're doing unconfined compression, we're putting that material under significant shear. That's actually how it's going to fail. So I think there's confusion about that. So the Young's modulus actually captures both the relationship between normal stress and normal strain and shear stress and shear strain. Because that sample is undergoing both normal loading and shear loading when I put it in a uniaxial device and compress it. If I want to have no shear stress, I have to compress that sample on all sides at the same time. So that's what we're going to do now. We're going to put a sample under isotropic compression. The way we would do this is we would take our sample and we would put it in a triaxial cell, right, surrounded by water, and just increase the cell pressure, but not put any other loads on it. So then it's going to have the pressure in all three directions, right? It's going to have sigma 1 is equal to sigma 2 is equal to sigma 3. So what was that Mohr circle like? Well, we're going to start off with a dot, right? And if I increase the cell pressure, what's going to happen to that Mohr circle? It's going to stay a dot because because sigma 1 is equal to sigma 2 is equal to sigma 3, or in this case we're only dealing with two of them. Sigma 1 is equal to sigma 3. So it remains a dot, but it moves to the right because the magnitude is going up, right? So this is what a PQ diagram for isotropic compression just looks like that. Just moves right along the p-axis and there's no Q. This is pure compression. And it is not the case that, in this case, that that epsilon, let's call it 1, is not equal to sigma divided by Young's modulus, because that's not the boundary conditions. If you want to think of another way, if I'm squeezing the sides so if I'm squeezing the sides while I'm pushing the top, I'm going to get more or less strain compared to if I was just pushing on top and not squeezing the sides. I'm going to get less, so obviously I can't have the same modulus, right? Okay. So in 3 dimensions, I just said this, but we looked at it in 2 dimensions. 3 dimensions, isotropic compression, sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to the mean stress. And in this case, the relationship between the volumetric strain, this is not the strain in the x and the y and the z directions, this is the total strain of the change in volume. So the volumetric strain, this is equal to delta V over V0. It's related to the mean stress divided by this elastic constant we call K, which is the bulk modulus. And the volumetric strain is what I just set up there, delta V, not delta V0. delta V over V0. And the bulk modulus is the elastic constant that directly relates the mean normal stress to the volumetric strain. So that's what that says. Now let's talk about simple shear loading. I'm going to take a cube and do this in 2 dimensions. First I'm going to isotropically load it out to some point because I want to have some stress on it before I start shearing it. Because in general cases with soils have no compressive force, they have no shear strength. So we're going to start with this isotropic compression we talked about. So I have, in that case, I've got sigma on both sides of it. And now I'm going to impart a pure shear onto it. And there's actually a way to do this test in the lab. It's a little complex, and I think if I just try and describe it to you verbally, you not get it. Maybe I'll remember next time to bring up pictures of a direct simple shear device. But I'm going to somehow magically just apply a shear stress on the 2 sides now that it's consolidated. So what's my Mohr circle going to do now? What's not going to change as I start putting a shear stress on it? Sigma 3 is not going to change, and sigma 1 is not going to change. So what part of my circle is not going to change? If sigma 1 and sigma 3 don't change, what part of the circle? Because my circle is going to change. The center is not going to change, right? If sigma 1 and sigma 3 don't change, then sigma 1 plus sigma 3 divided by 2 is still going to be the same value, right? So in this case, what's going to happen, I think I did it. Yeah, there it goes. As I start shearing it, what's actually going to happen, if I'm putting it in pure shear, is I'm going to increase the shear without increasing this sigma at this point. I shouldn't say sigma 1. This is sigma m, right? So this sigma m is going to stay constant. And all I'm going to do is grow my Mohr circle. So the actual stress is on the sides, but the mean stress is not going to change. So actually one of those is going to go up and one of those is going to go down, but I'm just going to apply a pure shear on it. So that's a pure shear loading.
So your sigma 1 and 3 still change?
Yeah, sigma 1, I should say sigma 1, the average isn't going to change. If I'm putting in a pure shear, I can't be changing the mean stress on it. So, well, I don't want to describe how a simple shear device works because it'll just confuse you. So there is, and the reason I describe that is because there's a modulus called the shear modulus that directly relates shear stress to shear strain. And so if you want to know what the shear, if you know the change in the shear stress, and you want to know what the change in shear strain is, you can just divide it by the modulus, and it works in all 3 dimensions. And because there's no coupling, because shear is different in the 3 directions, there's no coupling, so you can separate it in all 3 directions. So the point of this whole exercise is to give you an understanding of the difference between the bulk modulus and the shear modulus versus Young modulus and Poisson's ratio. We use Young's modulus and Poisson's ratio a lot in materials because they're kind of the first, because we can understand very easily how they relate to unconfined compression is easy to understand, and they were done early. But for many of our geotechnical problems, the shear modulus is more important. For instance, we do a lot of things with shear wave propagation. Anybody who's done earthquake engineering, right? We want to know about the shear wave propagation. Well, the shear waves propagate as proportional to the shear modulus. The P waves, which is the first wave that you feel from an earthquake, propagates in proportional to the bulk modulus because it's happening in an environment where there's just normal stress change. So now I said earlier how many elastic constants you needed to find a homogeneous linear elastic, isotropic linear elastic material? 2. And we just talked about 4, right? We talked about Young's modulus, Poisson's ratio, the bulk modulus, and the shear modulus. So that's how you relate to all these. And I put some other moduli that are going to be important to us later, like the constrained modulus. And there's a couple other moduli that you hear. There's, Lamb's constant, and there's another one. But they're ones that physicists use and some kind of engineering mechanics guys, but we basically never use them in our materials. But you'll see that there's 2 other moduli, Lamb's constant, and there's another one I can't think the name of right now because we never use them. But these 4 moduli that not moduli, 4 elastic constants that I put here are 4 that we use often. So you need to know Young's modulus and Poisson's ratio because you use them all the time. You need to understand shear modulus and bulk modulus because they really isolate shear behavior from compressive behavior. And then you need to understand the constrained modulus because it's a boundary condition that we encounter a lot in soils, and we'll talk about what the boundary condition is in just a little while. And I give you a printout of this page too. I think I uploaded it. So I think I gave you a PDF that just has this table. You can find this table in a lot of places, but okay, let's talk about compatibility of stress and strain. So if we undergo uniaxial loading, we're gonna write the stress-strain relationships in tensor notation is what we're gonna do right now. We have sigma 1 on the top, sigma 2 is equal to sigma 3, they're equal to 0. And we just got through defining all these. Epsilon 1 is going to be equal to sigma 1 divided by Young's modulus. Epsilon 2 is going to be equal to minus Poisson's ratio divided by Young's modulus times sigma 1. And epsilon 3 in the other direction is the same, right? Also equal to minus Poisson's ratio divided by Young's modulus times sigma 1. So I can write this. I'm going to do the shear loading. And remember, in shear loading, we said that the shear stress was equal to the shear strain. The shear strain was equal to the shear stress divided by the shear modulus. But if we want to write this stuff in terms of Young's modulus and Poisson's ratio, I can use that little substitution from that table. And so that's the same as the shear stress times that quantity 2 times 1 plus nu divided by Young's modulus. So all I'm doing is using that equivalence from the table. And similarly, I can do the shear stresses in the other two directions. They're the same thing. Well, these are all simple linear equations. If we want to put this in a matrix formation so we don't have to write down every one of these relationships all the time, then we can just put this all in a matrix, which is what we're going to do next. But I'll give you a minute to catch up with me. So I can put this in this matrix form, and we'll just look at one of these. And I'm having a font problem here. This should be a multiply there. But you know how to do this multiplication. You just write this is going to be, you take the vector and you put it over the top. So this would be just sigma x, this is sigma y, this is sigma z, this is tau yz, this is tau zx, and this is tau xy. And now you can just multiply them out. So we notice that epsilon x is going to be equal to 1 times sigma x minus Poisson's ratio times sigma y minus Poisson's ratio times sigma z, and zeros on the taus, all divided by 1e. And if we go back to here, we find out that's, right, you got epsilon 1 is equal to sigma 1 divided by e, but if I had loads in the other directions, I'm going to have to include these terms up there, and indeed that's exactly the way this comes out. So this is the transformation matrix between stress to strain. We call that the stiffness matrix. So this should be so the strains are equal to the stresses times the stiffness matrix, and we're using S for the stiffness matrix. So this is how you formulate, if you're writing a finite element program or something, this is how you formulate your matrix algebra. So this is just the way we get from the stress vector to the strain vectors through the stiffness matrix. Similarly, if we invert this matrix, I mean, lots of times you have the strains, you want to get the stresses. If you invert this matrix and you go in with strains, then that is called the compliance or the compatibility matrix, and it's just the inverse. C is that's not epsilon. C is just equal to the inverse. Oops, oh, it's right there. C is equal to the inverse of S. guess if I read my slide, I could do that. So that's a compatibility matrix. And I've conveniently written that one out for you so you don't have to copy it all down. Okay, let's talk about plane strain conditions. And first of all, let's talk about what are plane strain conditions. And I think I tried to load SketchUp on this machine and I couldn't load it up. So plane strain conditions are, well, we'll define it and then I'll see if I can draw a picture. So in plane strain conditions, the strains and stresses in the y direction, we're going to take z is down and x is one horizontal direction and y is the other horizontal direction. In plane strain conditions, the stresses and strains in all the y planes are the same. That's why we call it plane strain, because nothing's happening on those planes. So let me draw a picture of that. So there's like two real common conditions where there's a lot of places where we have plane strain conditions in soils. What are geotechnical loading conditions where we get plane strain conditions? It's anything that's really long and skinny. Yeah, so a continuous footing. So if I have a continuous footing, right, it's going to look like this. Right, sitting on the ground surface. And it's really long in this direction. Well, whatever's going on, so if everything is basically, if you want to think everything is the same in this direction, this is going to be the y direction. So everything's, let me be careful about this. This is going to be z in this case. This is going to be x, and this is going to be y. If nothing changes in the y direction, if everything's the same in the y direction, then what's ever happening on this particular plane here, for that plane extended all the way into the ground, has to be the same thing that's happening on this plane here. Down, so everything that's going on this plane has to be going on in this plane, right? If the loading's the same all the way along and it goes on essentially infinitely long in one direction, well, if everything's the same that's going on here, it's going on here, what can we say about the y stresses at this point versus the y stresses, sigma y at that point? They got to be the same. So what about the shear stress? What about any shear stresses that are in that plane? Well, there can't be any shear stresses. There can't be any shear stresses in this plane, because if there were, those two planes wouldn't be acting the same. Or in this plane, there can't be any shear stresses, because then we wouldn't have the same conditions at those 2 points, right? And so the other times you get this is a very long embankment, like a road. Or most of our slope stability problems are also plane strain problems, because in most of our slope stability problems, we have a slope here. Oops, didn't draw that very well. Right, and we're going to think about a section of the slope that might be failing. Look at a slip circle here. Well, whatever's going on in this one, we're assuming it's the same thing's going on in this one right here, right? So if there can't be any changes in this direction as the y direction, if what's going on, in this slice is the same thing that's going on in this slice, then the stress, all the y stresses must be the same, and there can't be any change in horizontal stress, so that the epsilon y has to be equal to 0, because if there was a change in strain in this direction, there would be a change in stress in that direction, and the shear stresses in this plane and in this plane have to be 0, or else I would have changes in the stresses in the y direction. So those are the two there's 3 cases, 2 I pointed out and 1 I described where you have plane strain conditions. So if we're in plane strain conditions, then epsilon y, there can't be any normal strain in the y direction, or else we'd have different stresses as we moved in y. And these 2 sets of shear stresses have to be equal to 0, otherwise we'd have deformation in the y direction. So let's apply those conditions to the stiffness matrix. So remember from our stiffness matrix that epsilon y was equal to minus nu times epsilon x plus minus nu times epsilon z plus sigma epsilon y all divided by Young's modulus, right? I'm just taking that one line out of the stiffness matrix. Well, and that's got to be equal to 0. So if I now solve for sigma y out of that, I find out that sigma y has got to be equal to, because that's the one we're interested in, right? Sigma y has got to be equal to nu times sigma x plus sigma z. Do you understand why we did this? All I'm saying is, I know there's no strain in the y direction, so given that, what's the equation for sigma y? Okay, so let's do some examples of uniaxial. Seems like there's a slide missing there. Or maybe not. So let's just look at what the implications of that are. So let's assume we have a K naught, a lateral earth pressure of 0.5 before we start loading, and I have a sigma z is equal to 180. So if K naught's equal to, and I'm ignoring effect, we assume we have no pore pressure. So ignoring the difference between the effective and total stress right now. Well, sigma x is going to be equal to half of that if K naught's equal to 0.5. So if that's the case, sigma x is going to be equal to 90. If the conditions are isotropic and sigma x was equal to sigma y, the stress tensor would be 90, 98, 180, right? What if I had plane strain conditions? Well, I'm putting this load one at the top, but I'm not allowing any strain in the y direction. Oh, I didn't type. And then the average, the mean normal stress, this is also equal to sigma m, is equal to 120, right? 90 plus 90 plus 80 divided by 3. Are you with me? So I basically loaded this thing, assuming I have K naught conditions, so there's going to be some strain in horizontal directions such that I get half the stresses in x and y directions are equal and equal to 90. There's my stress tensor, there's my mean normal stress. Let's do the same thing under plane strain conditions, assuming that I have K naught in the x direction, but in the y direction I have no strain. So in the x direction I've got sigma is equal to 90, and I have to assume a Poisson's ratio. So that equation we just had in the y direction, remember the sigma y is going to be equal to Poisson's ratio times sigma x plus sigma z, so that's going to be equal to 108. Notice that's higher than 90. It has to be higher than 90 because I'm not allowing it to strain in the y direction. There's no change in the y direction. So if I'm going to keep it from straining, I've got to add, it's got to be more stress, right? Now the stress tensor is 90, 108, 180. And notice that my mean normal stress is higher. Let's see, what's the next one? I don't remember what the next one is. Oh, the next one's with a higher, so I'll wait for that. So notice that if I assume I have plane strain conditions, I'm going to get a totally different stress. Totally different stress tensor. I'm going to get a different mean normal stress. I'm going to get different behavior. So when we have plane strain conditions, the soil sort of acts like it's stiffer, if you want to think about that. It's not that the soil's stiffer, it's the boundary conditions make it stiffer, because we're confining it in the y direction to not move. Well, when you're ever constraining something to not move, it's going to move less. So it's going to act in a stiffer fashion. What happens if we have a Poisson's ratio of 0.5? Poisson's ratio of 0.5 means what? Incompressible, right? Because however much strain you get in a vertical direction, you get half of it in the y direction, half in the z direction. So the material itself is not compressing. The volume is not changing. So what do you think? I have a higher or lower mean normal stress this time than I had when Poisson's ratio was 0.4? Is this a stiffer material or less stiff material? Poisson's ratio goes up. Is the material more or less stiff? In a volumetric sense. So I'm taking my, I had a dummy sample today. So if I got a Poisson's ratio of 0.5, we just said if I squeeze in the top, it's going to go out just as much as it went down, right? If it's got a Poisson's ratio of 0, I squeeze in the top, how much is it going to go out? None. Which one's going to have more volumetric strain? The one that went down and didn't go out, or the one that went down and went out some? Which one's got more strain? The one that went just down because the out's negative strain, right? One of them's got positive strain at the top and negative strain on the sides. The total volume change is one amount. The other one's got volume change on the top but no negative volume change on the side. It's going to have more total volume change. So as Poisson's ratio goes up, the stiffness goes up. Notice that the modulus, that Young's modulus doesn't have to change. You could have a constant Young's modulus, right? And as Poisson's ratio changes, the soil gets stiffer. Well, that's of course. Because Poisson's ratio is not the bulk modulus. It does not relate, the Poisson's ratio does not relate sigma, the mean normal stress, to the volumetric strain. That's the bulk modulus that does that. So, let's go back to my original question. Poisson's ratio here is higher than it is there. So in the end, and when we get done with this, I'm going to calculate the mean normal stress, P down here. Is it going to be higher or lower than this one? If I have the same, better be higher because I got, right? Let's see what happens. Whoops. I still haven't figured out why that happens when I do, how about I do that. Okay, so now, I guess I got to erase some of this stuff. Let me just erase it all. So now sigma y is equal to 0.5 times sigma x plus sigma z. All right, so that's now going to be 135 by 108. The stress tensor is now 90, 135, 180 instead of 90, 108, 180. And the mean normal stress is 90 plus 135 plus 180 divided by 3. It's 135 versus 126. That should make sense. When we do plane stress, we do a lot of things in 2D. The real point of this is we do a lot of things in 2D in soil mechanics. We don't really think about the third dimension. Well, the third dimension's there, and so we're making some assumption about the third dimension. We just do two-dimensional analysis. Normally, the time that's appropriate is when we have something that's really long compared to the width. We can make it infinitely long. What we're then saying is that plane strain conditions apply, and that we've got to know something about Poisson's ratio to understand what the stresses are in a horizontal stress. But it's not like there's no stress there. That wouldn't be plane strain conditions. That would be plane stress conditions. And so we've got to understand what it means when we make these assumptions. There is stress in the horizontal direction. How much stress there is in the y direction, how much stress there is in the y direction is going to depend on the stiffness of the material. And if we're using Young's modulus and Poisson's ratio, it's, the stiffness is actually a combination of Young's modulus and Poisson's ratio. If we're using bulk modulus and shear modulus, it would be just a function of the shear modulus. I mean, the bulk modulus, I'm sorry. I think we're really close to the end of this one. Let me see if I can figure that out. Because we're definitely at break time. Oh, yes. How about that? I love it when the plan comes together. Who said that? Dating myself. That's you guys probably don't even know who George Papard is. Anyway, so if a material is homogeneous, isotropic, and linear elastic, you only need two constants to describe it. Any two constants, but the ones we most commonly use are Young's modulus and Poisson's ratio, or the shear modulus and the bulk modulus. Or if we're going to do a one-dimensional compression, which we're going to talk a lot about here in a minute, it's the constrained modulus. The bulk modulus directly relates mean normal stress to volumetric strain. So if you really want to talk about, the way I like to think about it is, if you want to talk about normal stiffness, it's the bulk modulus you should be talking. If you want to talk about shear stiffness, you should be talking about the shear modulus. So the shear modulus tells you how much how easy it is to form in this direction. And the bulk modulus tells you how easy it is to squeeze the ball and make it smaller. Right? I like those conceptually. They have real meaning to me. Where Young's modulus is some weird combination of those two things, right? One's how stiff the frame is. Sorry, you structural engineers, right? One's how stiff the frame is, right? In earthquake stiffness, right? And the other one's how easy it is to squeeze the ball. But Young's modulus is some strange combination of those two things. It does relate how much a cylinder in uniaxial loading strains. But other than that, it's just something I don't really understand. So that's what that one says, except the part what I don't really, I mean, I can understand what it means for that cylinder of concrete in the testing device, but other than that, it does. In terms of state of stress in an infinite half space, it's just a constant that has something apart. It's a little bit of compression, a little bit of shear. The constrained modulus, we're going to get to this. Constrained modulus relates the vertical stress to the vertical strain in 1D compression. And I guess I didn't define that at all in this. We're going to define it in the next one, so I won't bother to do it right now. Any questions about, I hope that's done. Oh, plane strain conditions. Plane strain conditions, no lateral strain, epsilon y is equal to 0, and then 2 of your shear stresses are also equal to 0. All right, I think that's it. Cool. Questions about that?